All right, so now we are in part 3 of this, and we're going to talk about radicals now. Radicals have a really interesting history. I've read that Pythagoras was the first mathematician to ever discover or work with irrational numbers. I'm going to basically paraphrase his discovery. So you have a right triangle, right? And suppose the right triangle has legs of 1 and 1. And we want to solve for the hypotenuse. I'll just label that C. Okay, so hopefully you're familiar with the Pythagorean theorem that says a squared plus b squared equals c squared, which really is saying leg squared plus leg squared equals hypotenuse squared when you're dealing with a right triangle. So we're going to plug in 1 squared plus 1 squared, and we're going to say that equals c squared. Well, 1 squared plus 1 squared is 2 equals c squared. Now, to get rid of the c squared, we take the square root of each side. C equals the square root of 2. This number, the square root of 2, cannot be expressed as the ratio of 2 integers. And the book I read about this, excuse me, was very interesting because this really perplexed Pythagoras. Because at the time there were only integers. You had whole numbers, real numbers, natural number. You had natural numbers, whole numbers, and integers, and rational numbers. You had fractions. But to go into irrational numbers was completely uncharted territory, and there were all sorts of zany hijinks that ensued. That's what I have written here, that the solution to the above example is not rational. It cannot be expressed as a ratio of 2 integers, so now we're going to look at basically how to handle these radicals. So when we're simplifying radicals, all right, so we'll start off with something nice and easy. The square root of 100. The square root of 100 is 10. Because 10 squared is 100. Now, I'm sure there's somebody at home watching this saying, you forgot negative 10. I didn't forget negative 10. I'm just not including it. Because somebody's at home saying, well, if you do negative 10 squared, that also gives you 100. So why can't it be both? The reason it can't be both is because we're looking only for principal roots. All right, the principal root is the positive root. We're only interested in the positive root. In fact, if you were to graph the function f of x equals the square root of x, you get this. You only get positive answers. You don't get negative answers. And that's a whole other discussion for maybe a pre-calculus class. So I'll let your pre-calculus professor instructor handle that for you and lay down that level of math. We have bigger fish to fry right now. So if you have something like the square root of 16, the square root of 16 would be 4. 4 times 4 is 16. There's another example I have written in my own notes here that says the square root of the square root of 16. Well, the square root of this 16 is 4, so that would be 2. Let's look at 25 plus 144, and we're going to take the square root of that whole thing. Now, according to our order of operations that we talked about in the last video, we would add the 25 and the 144 first. 169 is the square root. We're going to take the square root of 169. Square root of 169 is 13. I'd like to compare this to the square root of 25 plus the square root of 144. So the square root of 25 is 5, plus the square root of 144 is 12. Now, I this is where a face-to-face class is kind of nice, because somebody would say, hey, wait a second, since these are radicals, can't you just add them? And the answer to that is no, because according to order of operations, a square root is an exponent. A square root is an exponent, so each of these square roots have to be carried out first before you can do your addition. So then 5 plus 12 is 17. So the moral I'd like you to take away from this is that a squared plus b squared under a square root is not equal to a squared plus b squared individually from each other. This is important. All right. Now, what do you do when you have something that's not a square root, like the square root of 72? So when you have something that's not a square root, like the square root of 72, well, most numbers have a perfect square living inside of them. All right, they have inside a perfect square. So it's just a matter of finding that perfect square. So if you go through all your perfect squares, all right, like our perfect squares, just to give you an idea, it's a fairly extensive list. 1, 4, 9, 16, 25, 36, 49, 64, 81, all right, it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 100, 121, 144, 169, 196, 225, 256 is 16. Yeah, that's as far as I can do in my head right now. There's 17, 18. So these are all perfect squares. So if you look at 72, you're going to look for a factor of 72 that's one of these perfect squares. The one that jumps out at me is 36. I know somebody's saying 9, and there's a reason you don't use 9. All right, and it'll be obvious when we do this. So if we do 36 times 2, 36 times 2 gives us 72. So now if we take the square root of 36, that's a 6 times the square root of 2. So the square root of 72 reduces to 6 square roots of 2. The reason we don't use a smaller number, like say, just as an aside here, if we were to do 9 times 8, 9 times 8 is 72, right? So if you do 9 times 8, the square root of 9 is 3, but now you've got the square root of 8. Well, guess what? The square root of 8 can be broken down to 4 times 2, times the 3. So then you have 3 times, well, the 4 becomes a 2, square roots of 2. You end up with 6 rad 2. So whenever you're simplifying a perfect square, you always want to go with the largest possible number, the largest possible perfect square. All right. I've got one more example I'd like us to do together. 243, a to the 5th, b to the 4th, and we're going to take the square root of this. So we have 3 things in here, so we're going to simplify 3 things. 1, 2, 3. All right. So 243 has its perfect square factor of 81. So 81 times 3 is 243. A to the 5th. We're going to break a to the 5th down to a to the 4th, a to the 1st. Oop, I should do this in blue. A to the 1st. A to the 1st. The ones that I'm writing in red are ones that are perfect squares. A to the 4th is a perfect square because if you take the square root of a to the 4th, you get a squared. B to the 4th by itself is a perfect square. So now we're going to take the square root of all of this. So sticking with my color coding here, 81 becomes a 9. A to the 4th becomes an a squared. B to the 4th becomes a b squared. The 2 left in blue are left over, 3a. And there you go. One thing I do want to touch on is that if you do the square root of a to the 6th, that's a to the 3rd. The square root of a to the 10th is a to the 5. All right. The reason for this is because of the rational exponent rule. When you have the square root of a to the 6th, this is a to the 6/2. The square root of a to the 10th is a to the 10/2. 10/2 is 5. 6/2 is 3. Okay, so that's what's going on there with those. So that's how to simplify radicals. In addition to simplifying radicals, we also have operations with radicals. So in this operations section, we're going to discuss the ideas of addition, subtraction, multiplication, and division. We're going to tackle those few. Okay, and division really is its own separate beast. All right. So if you had 5 radical 12 plus 2 radical 3. All right, well, these aren't like radicals, so you just can't combine them as you see fit. The radical 12 needs to be simplified. All right, radical 12 is 4 times 3, so it's 2 radical 3. So radical 12 is 2 radical 3. Times our 5 is going to make this 10 radical 3 plus 2 radical 3 will give us 12 radical 3 for an answer. Now, it doesn't really matter if you're adding or subtracting, it really is basically the same process. I've got one that's a little more meaty. 20 radical 72 a to the 3rd b to the 4th c minus 14 8 a to the 3rd b to the 4th c. Okay. So what's under these radicals needs to be simplified and simplified completely. Okay. I'll do this off to the side. So we already know 72 is a 6 rad 2, and we know 8 is 2 rad 2. We've already taken care of those. I want to tackle a to the 3rd, b to the 4th, c. Take care of these guys first. So a cubed, we're going to change to a squared a. b to the 4th is going to stay fine just the way it is. C is going to be just the way it is because it's just a c, you can't do anything to it. So this will become ab squared radical ac. This guy went out, that guy went out, those two remain inside. So we're going to have 20 times 6 ab squared radical 2ac minus 14 times 2ab squared radical 2ac. The 2 on the inside came from this 2, the 2 on the outside came from that 2, and then the ab squared rad ac came from over there. So 20 times 6 is 120. ab squared radical 2ac minus 28 ab squared radical 2ac. And now it's just a matter of combining like terms. 120 minus 28 is 92 ab squared radical 2ac. So that's addition and subtraction within those two examples. One that's somewhat benign, one that requires a little bit more work. I'd like to transition into multiplication. Multiplication is kind of nice because if you have 2 radical 3 times 4 radical 6, so long as the indexes are the same, you can multiply them. 4 times 2 is 8. Rad 3 times rad 6 is radical 18. And then you can reduce the radical 18. 9 times 2, so this would become 8 times 3 rad 2, giving us 24 radical 2 for the multiplication part of it. I'll do another one for you. 5 radical 3a times negative 4 radical 2a. So 5 times negative 4 is a negative 20. Square root of 2 times 3 is 6. A times a is a squared. Square root of a squared is an a, so negative 2a square root of 6. There you go. So here we've talked about addition, subtraction, and multiplication. I haven't talked too much about division yet. The reason for that is because division involves the rationalizing of denominators. If you're going to rationalize denominators, like if you had, well, we'll do an easy one, the square root of 6 divided by the square root of 3. Well, the square root of 6 over the square root of 3, since they're both radicals, both like radicals, 6 divided by 3 is 2. If it was the cube root of 6 divided by the square root of 3, this is done. Because this is a cube root, this is a square root, you can't do anything with them. Here you can do the operation, carry it out as you see fit. But what happens if it's the square root of 6 under the square root of 3? It's the reciprocal. You can still do the division, 1 over the square root of 2, because 3 over 6 is 1/2 and the square roots are just along for the ride. But there's an issue here, and really it's one of those things that pains me because outside of pre-calc, in fact, outside of this class, I really can't think of a time where you'd ever absolutely have to rationalize a denominator. I also teach calculus and pre-calculus and statistics, and in calc and pre-calc, I accept this as an answer. I don't worry about students rationalizing denominators because there really is no reason why you'd ever have to rationalize a denominator, truth be told. But regardless, you need to get rid of that radical because that's the class we're in. So to get rid of it, you know how up here we said the square root of a times the square root of a is a squared, which just became an a? We're going to take advantage of that. All right, we're going to take advantage of that. If you have rad x times rad x, that just becomes x. We're going to exploit this. So if we have the square root of 2 times the square root of 2, well, that's just going to become 2. So now we have 1 times the square root of 2 is the square root of 2. Radical 2 times radical 2 is 2. Now that's been rationalized. There's your answer. It becomes a little more tricky when you have something like 4 over 1 minus, or 1 plus the square root of 5. This becomes a little bit more involved when you have an example like 4 over 1 plus the square root of 5. Here we need to employ something that we call the conjugate. So we're going to multiply by 1 minus the square root of 5 over 1 minus the square root of 5. So that when we multiply these, 1 minus the square root of 5 plus the square root of 5 minus 5. These middle terms cancel out. 1 minus 5 is a negative 4 over 4 times 1 minus the square root of 5. Those guys cancel out, giving us just a negative 1, and there's our solution. All right. So whether you have a monomial or whether you have 1 term or 2 terms in the denominator, this is more or less carried out the same way. So we're going to pause this here, and we're going to come back to rational exponents in the next video.